Hello and welcome to my presentation on HTTP3. My name is Brian Sletten, and today I'll be talking about HTTP3 and its impact on performance of web-related applications. But it's also a talk that's a little bit about how do you go about approaching evaluating where performance issues can be addressed with your system and how you go about doing them. So there's really two levels that we're going to talk about the concepts of evolving the protocol of one of the most popular application level systems that we use on a daily basis. I have been involved in the IT industry for about 30 years and recently have written a couple of books on WebAssembly. And most of what I do is looking at the future and how things are evolving and where things are going, but from a practical perspective and how these technologies go about actually solving problems for us on a day-to-day basis. So when you approach a performance issue, you have a lot of options in how you decide to appeal to the need to address these. And the very obvious thing for developers is to focus on perhaps the language choice and its implications in terms of performance. While you might be drawn towards Python because of its clean syntax and friendly development environment and a wealthy ecosystem of modules to have available to you, as you can see, out of the box, it is not a very performant language. And so if you wanted to address that, you would generally have to imagine re-implementing it in a different language. And you can see the simple approach of moving from Python to Java for the same algorithmic code base in this paper takes you from 25,000 seconds to accomplish a computationally intensive task to about a tenth of that. And then going to C would make it even much faster. Once you move to a higher performance language like C, then you have options to do some hand optimization around unrolling loops and parallelizing the activity and whatnot. But the problem as we go increasingly faster and faster and faster, you can see what kind of amazing performance gains you can get. But the skills to do that kind of coding are outside of the reach of most developers. They just don't have the background in them. But even if they did, we don't want to rewrite everything all the time, right? There's so much software to be written and so many problems to solve. We can't spend our time rewriting everything. And so we want to look at other options for how can we go about improving performance. And one of the approaches that I've found interesting in, for example, the implementation of TensorFlow.js, which is a JavaScript-based machine learning system that Google produced, which seems like a weird concept, right? JavaScript is not a high-performance system. It doesn't generally have, especially in the browser, access to hardware to accelerate the activities that we normally expect to do with machine learning. But what they decided to do was to focus on developing very clean, stable APIs. These are represented by the orange diamonds in this diagram. But then to have pluggable backends that hide the details of the implementation of where the engine is going to get its performance. There's a default JavaScript CPU-only backend that runs terribly everywhere. And then if you're in the browser, they can do a trick that people used to do back in the early to mid-90s, which is to pretend like they're doing 3D graphics in order to get access to the hardware that might be available on your machine. Every browser supports WebGL, so this is an indirect way through the shader language to get access to the GPU. But notice that there's no real difference for the application developer who's building the TensorFlow application to be able to need to focus on that. It's just a different backend that gets registered when the application runs. Likewise, if you take a TensorFlow.js application and move it into an environment like Node, where there are fewer restrictions than you have in the browser, you can imagine different pluggable backends tuning to particular environments. For example, if you have a server, it's very unlikely you're going to have a CPU or a GPU, but you might have a pretty powerful server CPU. So a backend that does well with those sorts of vectorizing instruction sets and things might definitely have a huge performance improvement over the straight JavaScript general CPU implementation. You might have access to the GPU through CUDA or some other kind of native library. And if you're Google, they have the TPUs that they're rolling out for modern large language models and things like that to speed up the performance. So the benefit of this approach is we're not rewriting the code in the language as the application developers, but we are relying on our framework providers doing the rewriting for us in many ways. And therefore, we don't have to think about it. We don't have to feature test our applications to say, am I running in a browser? Do I have access to a GPU? Do I have access to some multi-CPU kinds of configurations? So that puts the burden on the implementer of the framework, not on the application developer. And that's a nice step forward. One of the most obvious impacts of this is that the application itself doesn't change, but you can see we can have similar sorts of performance improvements, going from about close to 3.5 seconds to do a facial detection kind of activity to a fairly pedestrian, mediocre integrated GPU like the Intel Iris GPUs that have been found on conventionally in MacBook Pros and things like that. We could go from 3,000 milliseconds down to 49. And if you run it on a beefier desktop box, you can see we can get down to like 5 milliseconds. And if you run in an environment with access to native CPU vectorization instructions or libraries like CUDA, we can have an equivalent of 1,000 times speed up without us having to do anything in our application. So if you can take advantage of an environment like that, that's great. The potential benefit that extra GPUs are going to give you, though, is going to be a function of the nature of the application problem that you're dealing with. This is famously encoded in Amdahl's law, which shows that if you have a problem that has a large capacity for parallelization, then throwing more processors at it helps it. But if you don't have the problem, if it doesn't break up nicely into parallelizable activities, then throwing more CPUs at this or more GPU cores at this is not going to speed it up. So we're limited in the application of faster parallelizing and vectorizing hardware based on the nature of the problem that you're dealing with. One of the next things that the TensorFlow.js team did was to focus on a WebAssembly implementation. And this may seem a little bit strange given the performance improvements we've already seen, but the benefit of the WebAssembly implementation is that they don't have to rewrite anything. They could take an existing C++ based neural network infrastructure, recompile it to WebAssembly, and gain a lot of ahead of time optimization performance that is not available in the JavaScript environment. And notice now we can see an equivalent, or at least within the ballpark kind of performance speed up that we got with using the WebGL implementation within the browser across a wide range of hardware. So what this implementation does allows us to reuse existing code without having to rewrite it, and yet still get performance improvements on a wide range of hardware, including, in this case, some that don't actually have GPUs or modern CPUs, but still have reasonably powerful performance CPUs in the back end. Architecture can often be used as a tool for performance gains. Famously, the REST architectural style is a stateless client-server system. Therefore, the clients don't necessarily have to be tied to a particular server. And just like if you go to a restaurant and the line gets long, while you're waiting to place your order, if the manager opens up another cash register, you can go through basically twice as fast. So architecture gives us the ability to improve the performance by reducing the burden on any particular server and spreading it out across a range of available resources that are available to us. But that simple horizontal replication obviously will run into some limitations where not everything is going to need to be replicated. And so a more efficient way of leveraging these additional resources is to scale based on functional needs. This is famously described in this art of scalability book as the performance cube, where the horizontal duplication is one dimension of performance improvement, whereas being able to scale things based on functional needs, which parts of it actually need to be scaled, is the next step. And this is where architectural choices like microservices can start to help by allowing you to tune the need for scaling at a particular part of your implementation so that you scale only what is needed there, and eventually that gives you a more efficient use of the hardware that you have available to you. But then we start looking at the reality of particularly web applications that we're building. They're being deployed into this crazy complicated ecosystem of different clients, different servers, different technologies, different implementations, and somehow it all works. But built into this is the need to address the concept of latency. And obviously, when we're establishing connections on a web application-based nature, the latency of the setup costs compound depending on the nature of the interaction of the application. And what we find ourselves in the 21st century, as we now have 30 years of web experience under our belt, is that we're moving away from a purely document-oriented view of the world to a much more interactive services, applications, and kind of dynamic environment, in which case the communication patterns are more robust, more complicated, and we're going back and forth, whether we're using single-page applications or sort of more conventional reactive-based systems. And that latency is going to compound over and over and over again. HTTP was designed in a very different time, and there are a lot of limitations that are intrinsic to its design that have been modified over time. And that's why we're going to talk about HTTP 3 now, because this is not necessarily one of the things that you think is going to be available to you, and maybe directly it's not. But because the standards engineers at the IETF and the W3C spend time evaluating these kinds of systems, they can find performance problems in our application infrastructures that we can take advantage of by migrating to newer versions of the protocols. Because we're also moving towards a new world where everything is encrypted. And even after you go through the SYN-ACK three-way round-trip way of establishing a TCP connection, because of the layering of the architecture, we then have the TLS handshake to set up, which historically has involved many more round trips. And therefore, the cost of setting up a connection to issue an HTTP request is already many round trips into the cost of the performance. And therefore, if we need to use a connection, we want to amortize the cost over the lifetime of the connection, as opposed to opening up lots of little connections, which is what we have done in the past. So we have the benefit of thinking about these protocols in the way of applications sending horizontal messages to each other, but they will be implemented based on the vertical services of the network technology stack that's available to us. And therefore, we don't really have a lot of control or visibility into what's going on under us, but we can still focus on how do we establish the connection and how do we handle the efficiencies of the messages. Because remember, TCP is a reusable transport level mechanism for managing connections across different types of applications. And therefore, it has built into it certain safeguards, so no particular application can inordinately consume more bandwidth than is available or is due it as one of many applications participating on the network. So TCP has things like slow start and congestion control that if you're not using the connection, or if you're running into bandwidth problems, buffering problems, resending of packet problems, then the congestion window will close and not give you access to as much bandwidth as you need. And given the bursty nature of HTTP, there's been this intrinsic impedance between the application level use of the network connection and what the network connection is doing because of its layered leanings, right? We're reusing different kinds of applications across multiple types of activities. So originally, HTTP was text only. So that's built into it a performance issue when we start moving to support images. Originally, HTTP 09 did not support images. It only supported text-based GETs. So it wasn't a huge issue, but it did assume that you would close the connection when you finished retrieving the document that you asked for. So think how that would be a problem in the modern world if every connection you made to ask for an individual HTML file or an image or a JavaScript file or a style sheet or a WebAssembly module, open up the connection, pay the penalty, get what you need, close it, repeat. So in order to deal with that, HTTP 1.1 added support for keep alive. We can keep the connection alive and therefore use the connection for longer and get more benefit out of doing so. We also added in HTTP 1.1 the ability to support pipelining, which means asking for multiple things at once. That avoids some of the round-trip latency that we deal with when we do it one at a time. But the problem is it's still a request-response-based system, and therefore what we end up getting back is limited to the one at a time handling, which means we have head-of-line blocking. To get around this problem, developers were often encouraged to open up multiple connections, which then means we're paying the setup costs and the congestion control impedances multiple times per application rather than just once. And as I said, the congestion control is part of the remaining impedance mismatch between HTTP as an application protocol and TCP as a reusable mechanism for managing connections. So HTTP2 tried to address this problem. Rather than relying on the head-of-line blocking, rather than requiring request-response latency that involves wall clock time increasing as we ask for the first thing, get the response, ask for the next thing, get the response. Instead, we have a new framing layer that allows us to express these things as binary, bidirectional, asynchronous channels, which means we can have prioritization of streams. Streams are really just a construct for scoping particular interactions. So as the client asks for something, it'll create a new stream. As the server finishes responding it, we will close the stream. It's not like closing a connection. This is really just sort of like a virtual segmentation of our use of the connection. But notice we can also interleave the responses, so we no longer have head-of-line blocking at the application level, at the message handling level. But we also then have redundancy in the fact that the application level is now managing frames of streams, which are the subsegments of the streams, and if something needs to be resent, it will resend it at that level, which is redundant to what's happening at the TCP connection management level. So even though HTTP2 was a huge leap forward, it was not as successful as we wanted to, and that's where QUIC comes in. HTTP3, quite famously, is abandoning TCP. We're avoiding the impedance mismatch of the TCP congestion control. We are avoiding the need to have two different handshakes, right? We have layered handshakes at the connection management level and at the TLS establishment level. So it's going to merge those into a single handshake that both establishes the connections and initiates the encrypted communication. They chose to implement this based on UDP rather than TCP, but UDP was insufficient in terms of its overall capabilities, so QUIC is a layer on top of UDP, as you'll see in just a moment. They're also moving away from identifying connections based on the combination of IP address and port number into a connection ID, which acknowledges the fact that we are a more mobile user base these days, and we might move from network to network throughout our use of a particular connection. So this gives us more visibility into the establishment and reuse of the connection over a wider variety of network scenarios. And even though we solve the head-of-line blocking at the messaging level, because of the layering, again, we still have head-of-line, we still have the concern about a packet needing to be resend, blocking any other packets from being handled. And so QUIC also introduces the notion of streams at the connection level, not at the application level, and each individual request is independent, and a resending of stream elements does not block any other streams. So we're no longer required to handle the connection management at the level below where we're working, which is the case when we were using the reusable transport protocol TCP. So you may wonder, why did we have to do this? And as I said, it has to do with the fact that we are dealing with more interactive applications, less document-oriented things. We have existing infrastructure that's out there that's designed to support and filter and route things at particular levels. And therefore, we needed to build it on top of something that would already be allowed through these firewalls. And UDP is currently generally in that category. So QUIC doesn't introduce anything that should block UDP packets at the firewall level, but we also can avoid some of the redundancy of the connection management, the message handling, et cetera, as I said, while also supporting mobile migration of users moving from network to network. So we have this new layer that merges encryption, merges connection management, builds on top of UDP, and allows us to get better reuse, better congestion control, better error handling, and overall just a great sense of performance improvements that you will benefit from simply by using it. So we can imagine now that rather than multiple round trips, the first contact between a client and server is called the inchoate client hello. And that says, hey, I'm here and I'd like to talk to you. And the server's like, nope, you need to tell me more about who you are. But in that process, the server will provide its encryption credentials, which the client will then use and establish the connection and have the ability to issue encrypted requests. And at that point, we have a one round trip handshake as opposed to multiple handshakes with multiple round trips. On subsequent interactions, if the client caches the credentials of the server, it can simply start up where it left off. And as long as the session is still valid, we have what's called a zero handshake, or zero round trip handshake. So you can imagine reducing the multiple round trips to zero has significant impact on our performance. And if for some reason the session is no longer valid, then the server will just reject the cached credentials and go through the whole process again. But it still becomes just a one round trip handshake at that point. So how does this translate? We have TCP versus QUIC. The all line represents both 1 and 0 round trip scenarios, whereas the QUIC with the 1 round trip line is just the 1 round trip without the 0 restart. And you can see that when we look at the combined 0 and 1 round trip sessions, it is still substantially faster than the TCP space. But when we factor in the 0 round trip ones, we can see how much flatter the establishment of the initial handshake is over increasingly high latency round trips. And so the penalty is not compounded in the way that it is in establishing TCP connections when we have the benefit of relying on the 0 round trip. And then because this is a reusable protocol across multiple applications, we can see that across a wide range of application uses like search or video latency, establishing streams on YouTube versus getting search results from Google, we see substantial improvements in the performance of setting these connections up. And even in situations where the network connection is maybe flaky or bandwidth becomes a problem, so it's not a question of establishing the handshake, we still see benefits because we have better error handling requests in response to the latency, and the error reestablishment in the use of the connection. So basically, what I want you to know is that this is coming. It is in the process of being standardized. QUIC has already been standardized. HTTP3 is moving to in this direction in the relatively near future. By sometime next year, we should have more and more activity in this space, but there are already implementations. If you go to QUIC working group, QUICWG.org, you can start to see the specifications and the implementations that we're already going through. So I hope you enjoyed this. I hope you found it interesting and encourages you to think beyond just changing your language or relying on architecture, but to actually look at the whole system and the protocols and the network infrastructure that's there. You may not be able to individually direct changes to improve the performance, but because industry standards are moving in this direction, you will benefit by adopting it. Thank you very much, and feel free to reach out and contact me if you have any questions, and enjoy the rest of the conference.